And so with that, I'm going to turn it over to Bill Magro, the CTO and Director for HPC at Google, to talk a little bit, give you a preview of where Google stands right now. And we're going to dive into this much more in a later session.
Thanks, Jay. I really appreciate the introduction. So I think one of the questions that people are wondering is, around high performance computing in cloud, which is, if you look at the current market or the latest market research, this is from Hyperion. Bob is on the call, so he's probably going to talk about this more. But we can see that high performance computing spending has reached about $8.7 billion this year, which is about half of the traditional on-prem infrastructure. And then, of course, that infrastructure and this spending represents about half of the overall spending in high performance computing. And so it's natural to ask the question, why so much, but also why so little? And so I want to dive into that a little bit. So why so much? One thing is that cloud is providing ways for people to augment their on-prem. I think this is something that's very different. You'll hear from Google than maybe some other cloud providers, is we don't necessarily show up and say, cloud can solve all your problems. There's a place for cloud, there's a place for on-premise. We respect that. We really see cloud as something that can make all of us more capable in our jobs, whether we're responsible for providing high performance computing capabilities to the users, the scientists and engineers, or we're the scientists and engineers who now can get their work done faster. So there's a number of different ways that cloud augments on-premise systems. Some of those are enumerated here, not all, but a lot of that's what we're going to get into in this community, is understanding where cloud fits, not saying it's only cloud. So clearly things like accessing the latest hardware technologies. I think everybody knows that getting access to the latest technology is getting harder and harder, but it often appears first in cloud. Also recognizing that we all have really the world of choice when we buy things for on-prem, but ultimately if you want to solve the hardest problems, you have to bring a certain amount of homogeneity into your system. And that means that you're leaving certain problems maybe underserved. So being able to access the diversity of hardware and services in cloud to complement the choices you make on-prem is a very powerful reason that people choose cloud. Just accelerating R&D by being able to put some new resources out there for a team without disrupting things that are business critical. So enabling exploration without taking on the opportunity cost of disrupting the business critical things. I think if we look at areas like automotive design, weather forecasting, these are very common problems where you want to innovate, but you don't want to disrupt what's going on. And of course, I think we all know that quantum analytics and AI are all new capabilities and growing capabilities where things are changing very, very fast. It's very difficult to stay at the leading edge on-prem, but through cloud, you can get a slice of those capabilities and see what they'll do for you. And that's another powerful reason to bring cloud into your mix. So all of these things have been driving people to adopt cloud, and there's some of the forces that have driven up the spending. And if you look at the growth of the HPC market, it's actually very encouraging. Both on-premise and cloud spending is growing at a very significant clip. I think Bob can tell us the specific numbers, but I recall seeing about 20% year-on-year growth. So it's also natural to ask the question of why not more cloud, right? And so if you look back at maybe a decade or more, where did cloud fit? I like to look at it through the lens of this graph that I made a couple of years ago, which is if you think about the capability, the hardest problem that you're trying to solve with a supercomputer, and you look at the number one systems on the top 500, I like to define capability equal to their capacity. If there's I build the biggest system I can to solve the hardest problem I have. Therefore, it's a capability system. So its capacity and its capability, are equal. And so therefore you can plot all of the number one systems from back 93 through a couple of years ago and where they land. And then the question is, what do you do with more capability or more capacity? Certainly at the high end of HPC, people solve harder and harder problems, advancing the hardest problems in science, because there's still many unsolved, what we used to call grand challenge problems out there. But in many other use cases, having more capacity is actually more useful to do things like design of experiments and in design space exploration. Think about ensembles and weather forecasting. You don't necessarily build the highest precision model you can, you run more models and you get greater insights. So maybe 10 years ago, cloud was good for getting access to a single machine, and you could run some of those throughput-oriented problems that maybe show up in industries like electronics, and later in some of the stuff in automotive. But as you get to the harder and harder problems, we get pushed back up. So essentially, cloud offered what many considered unlimited capacity, but the problems that it could solve were relatively limited. So that was certainly a barrier and has been a barrier to adoption. Others ones include just the complexity of cloud. It's a whole new set of interfaces, a whole new way of thinking. And how do we knock that down? Data movement remains a really critical problem, especially if you're using cloud services in conjunction with on-premise. So what are we doing as an industry and a community to attack those problems? And finally, cost. I think if anyone goes and looks, they'll see if they try to do the exact same thing they do with a large-scale on-premise HPC system that's fully utilized, it's going to cost more to do exactly the same thing in cloud. So why would you do that? It has to be to get access to the things that we talked about before, the things that complement that you can't do on-premise or can't do at least simultaneously with the choices you make today on-premise. So as we look forward, how is cloud changing? A lot of what's been going on over the last decade across all cloud providers, and Google Cloud will share you with what we've been doing on that front, is removing some of those scalability and efficiency barriers. And what this means is cloud's capabilities are going up. It comes through emphasis on tuning message passing libraries. It comes through tuning the machines so that they behave the way you expect, like bare metal, and libraries run correctly. It involves things like bringing in RDMA technologies for very high performance message passing, which Google announced is coming in our next generation HPC virtual machine types just before supercomputing. It involves bringing in changes to the way cloud resources are orchestrated so that you can actually provision a true supercomputer behind the scenes versus an API that gives you a collection of machines that could be anywhere in the world. Bringing in parallel file systems. There's just a wide range of things that we're doing to actually elevate the capability of cloud. And this isn't to say that now you will solve all those same problems in cloud. It's that you now have the option. And so you can reason about where is the best place to solve your problems. On-premise, on cloud, with traditional schedulers, with MPI, by recasting your application in a cloud-native format. And we're going to have people come in and share with you how they've done that and really gotten breakthroughs in performance and scalability. So the point now is that it's an option to do a lot more problems in cloud than you might know. And we're going to get into that in this community for sure. So there's a lot we've invested in Google Cloud over the last several years, going back almost a decade in many cases. Clearly, we're not going to talk about that today. That's not the focus. But I want to call your attention to a few things. One is that people who provide HPC, and we put them at the bottom, we're calling them admins, really want to comprehend and reason about how to use cloud, sometimes multi-cloud, on-premise, whether to go with container-based or traditional VM-based, how to expose that up and what are the services so that they can present not only capable HPC systems to their users, but also be able to offer more choices. The burden on someone who provides HPC services can be quite high, especially if you have to do it all. And through automation and a lot of integrations, it's possible now to actually, I'll say, enhance your offering and become more valuable to your users because of all the things you can do. And cloud enables some of that. A big concern, I think, of the HPC community has been, was cloud a threat to my job? And we see it as just the opposite. If you're providing HPC services, cloud provides you a whole new set of tools, access to new technologies, and you can become a superstar for your user. And so that brings us to the top of this slide, which is users, especially scientists and engineers, really don't want to know about infrastructure in most cases. They just want to be able to interface, whether it's through traditional schedulers and command lines or remote workstations or Jupyter notebooks, or even write flows that are based on APIs. They want to get their work done. And so a lot of where our work is, and a lot of what we'll talk about in this community, is what's happening in the middle from Google, its partners, and the community to connect these two ends and really advance the time to insight. So when we come together next week, we will deep dive into a lot of what's on this slide and the specifics of how we're elevating scalability and how we're easing access and making it simple to create turnkey environments. But we'll also touch on other things. So going beyond traditional HPC, you saw the same graphic earlier in Jay's intro, but I'd like to talk a little more about it. I think we all recognize that AI, in particular machine learning training, is an HPC workload. And so we need to make sure that that runs well. And I think all the excitement around AI has really advanced our capabilities in the cloud and accelerated them. And we're going to be excited to share with you that. And that doesn't just benefit ML training, it benefits HPC more broadly. AI in the workflow. Everybody's looking at how AI and agents can help us become more productive while we do traditional modeling and simulation. But the real excitement, I think, is what's happening in the upper right corner. And in particular, if you've been following what's happening in the community, I'll give you an example from Google. Google's DeepMind has published a lot of papers in Science around weather forecasting, protein folding, DFT, density functional theory, and materials discovery, even Nobel Prize this year for some of that work, for some of our Google DeepMind people. So we'll be bringing them in to share not only the techniques and the innovations, but what we're doing in Google Cloud to make it more accessible to this community. Another exciting area Jay mentioned is quantum. Google has laid out a roadmap of milestones of what does it take to get to a usable, effective, capable quantum computer to complement traditional high performance computing and modeling and simulation. Some of these milestones have been hit and some of them lie ahead, and we'll be bringing in experts from our Google Quantum to talk about that. And on both of these topics, the AI and the quantum, we'll be bringing in partners as well to talk about what they're doing, because Google Cloud is open and we believe in multi-cloud, we believe in open source and open solutions. So to wrap up, just as we look forward, these are the kind of talks that you're going to hear about in this community. Certainly from Google, you're going to hear about our core HPC technologies, which is your message passing, your compute network storaging, CPUs, GPUs, TPUs. In fact, the Seymour Cray Award recently went to Norm Chupi for innovations in AI, specialized AI infrastructure. That's Google's TPUs are part of that. The large-scale data analytics, and as I mentioned, our DeepMind and quantum computing. From our partners, though, we're going to hear from NVIDIA early in the year, leaders there, about their view of the future of ML and HPC and how do we advance HPC capabilities without HPC getting left behind, a common concern in the industry. We're going to hear from our partners who are creating their own automations and platforms and services for science and engineering built cloud native, and of course our quantum and AI partners. And then of course we want to hear from all of you on your most innovative uses of cloud and HPC, your best practices, how you're achieving your sustainability goals by running on the clean cloud, which tends to be the cleanest way to do high performance computing. And of course, more from folks like Addison and Bob around industry analysis and insights. And so with that, I'd actually like to hand it over to, I think Addison is next. Is that right, Jay?
Yeah, so now we're going to have a conversation between Addison Snell of Intersect 360 Research and Bob Sorensen of Hyperion Research. And they're going to recap some of the SC24 highlights they noted being analysts in this industry and give us some pointers to some things to look at in the community going forward in 2025. So with that, Addison, you want to come on screen and introduce yourself?
Yeah, sure. Hi, everybody. I'm Addison Snell with Intersect 360 Research. We're industry analysts who track high performance and data center markets, and that's included putting together our new HPC AI leadership organization, or HALO. I have a podcast, This Week in HPC, as you can see on this nifty AI generated chart. I didn't include a personal fact about myself, but I do rather enjoy crossword puzzles, and I've had a few published in my time. So that's me, and why don't we introduce Bob as well?
Yeah, hi. Thanks, Addison. Addison should point out that the day that El Capitan was announced at SC24, I believe it was an answer in a New York Times crossword puzzle. So one has to chalk it up just to serendipity, or no, it was all pre-planned. So yeah, I'm Bob Sorensen. I'm an analyst here at Hyperion Research. We do HPC stuff, and I have the really cool job of looking at the bright, shiny objects in advanced computing. So as GPUs came along, we tried to figure out how they fit into the advanced computing environment as things like decisions about moving to the cloud or staying on-prem, things with quantum computing, things with what's going on in AI, and right now the cause celeb, if you will, some of the interesting developments in generative AI, some of the large training requirements, and its impact on both enterprise applications and both of this and the science and engineering community as well. So to me, as I like to say, in the old days it was simple. You had two choices: you bought a Cray or you didn't. Now there are so many options. There's so many ways to get it right, and there's just so many ways to get it wrong. And if you get it wrong, the penalties are huge. And so understanding the problems and trying to figure out exactly what the questions an end user needs to ask, and really the questions in my mind always should revolve around workloads. What are the workloads you have, and what is the architecture, what's the option, what is the installation or the strategic plan you need to have to address those workloads, and more importantly, what are the key performance indicators that really matter to you? And I always like to point out that, in the old days when machines were hugely expensive and people were cheap, people talked about utilization. Oh, my machine runs 98% utilization. Well, if your average queue wait time is 13 hours, you're wasting a lot of PhD researchers sitting around, even though you're very proud about high utilization. Key performance indicators should reflect increasingly time to science as opposed to time to job turnaround. So I'll stop there. And Addison, did you want to kick off your first SC insight of the day?
Yeah, well, I mean, I was delighted that they invited the two of us to talk about SC24, and Bob and I talked offline and said, why don't we just have a conversation about it as opposed to two separate 10-minute presentations, which would be a little silly. And Bob, I'm glad you mentioned El Capitan, because I think most supercomputings, we would go in and a new #1 supercomputer would be the big news from the show. And this is a stunning, beautiful, gorgeous new supercomputer at Lawrence Livermore National Labs from which we're going to get tons of scientific insights. But Bob, for me, it was almost like that wasn't where the energy was this last show. It was like, yeah, here's this great new supercomputer, but next to everything going on with AI and hyperscale, it's almost like, wow, you've got this couple $100 million supercomputer and it's whatever, 30, 50 megawatts. Good for you. That I love that for you, your little supercomputer. Was it almost like an afterthought compared to what's going on with these huge AI supercomputers and hyperscale?
I thought we were going to have some point of disagreement here. I was thrilled that the enthusiasm was nearly as we've seen in the old days. I mean, we're talking about, and I hate to use the phrase, this is almost like an evolutionary dead end. The homogeneous architecture, $600 million, multi-megawatt kinds of systems that takes 4 years to design, 4 years to operate, and 2 years to tear down. I believe that we are in kind of entering a phase of Neo-Exascale. What are the next generation kind of HPC architectures going to look like? And to me, I view those 3 Department of Energy procurements as the last of the, as I said, the homogeneous architectures. I think if you look at what your HPC is doing, the first European exascale system going, the Jupiter system going into Germany shortly. Exactly. Partitioned architecture, CPU-centric, GPU-centric, experimental processor partition, a quantum partition coming shortly, as well as a cloud partition. It goes to my theme of workloads dictate architectures. Architecture shouldn't dictate workloads. And so I think we're going to see a much more sophisticated partitioned architecture. And relevant to this conversation, it's not just about on-prem decision-making anymore. And it's not just about should we migrate to the cloud. It's how do we generate an integrated hybrid on-prem cloud infrastructure that meets all of our workload requirements effectively. And 2 simple points to make there. How do you benchmark a procurement that's a hybrid on-prem cloud activity? And how do you budget for something like that? One, you have to budget for 5 or 6 years of a procurement lifetime cycle. Another one, you could be doing a month-by-month thing. There's a lot of work that needs to be done, I think, for an HPC end user to generate an effective, sophisticated mix of on-prem and cloud going forward. So it's no longer where do we live, it's we got to live everywhere. And I think I started to see that at SC, that idea.
Yeah, I really like that in the discussion that Bill and Jay led prior to this is, the evolution with cloud. It's really, the talk has gone from why everything should be in the cloud to when should things be in the cloud, right? How are we going to use cloud as a complement to on-premises computing, both in terms of capability and in terms of cost? But I think when you talk about these modular supercomputers going forward, there are a lot of different industry dynamics at play when we look at the influence of AI vis-a-vis HPC. One of them went into the Q&A here about precision and processing elements. I think that's absolutely right on. When we look at accelerator roadmaps going forward in the future of 64-bit computing, This is where top 500 really does have some influence, is that HPL score is at least a 64-bit score. And when we talk about something vague like AI flops, I used to know how much a flop was, and now I don't anymore, right? We're getting into mixed precision, low precision, emulation of FP64 using int8. Is that going to be something we're doing in HPC or not doing in HPC? We've been through this kind of transition before when we migrated from large SMPs to clusters. A lot of people talked about, well, that's not the most efficient way to do high performance computing. There were some enthusiasts, and ultimately the clusters won from a cost performance standpoint. And everyone had to kind of go into MPI. I think the difference there is that was largely end user driven. Whereas this movement around precision and what's going on with the processing elements is largely supply side driven. And there's a question of, is HPC going to have to start migrating down to these lower precisions?
I think you're exactly right. There is some concern in the CPU only crowd about what happens to 64-bit floating point. Remember, that was just a number that the IEEE picked to gather the fact that almost all mainframe vendors at the time had different formats, and there's nothing terribly sacred about 64-bit precision, other than it's a nice round power of 2. I think that there is a lot of opportunity for organizations to start to really think about how much precision they need during the entire workflow. And the reason I believe that is, I think people start to have to see the handwriting on the wall, which is AI and GPUs are driving mixed precision hardware developments. And so if you stick to 64-bit, you're going to start falling by the wayside in terms of, I can't go out and buy a chip that has the same amount of 64-bit hardware horsepower as if I dropped to 32 or 16. So I think it's time for organizations to start to rework some of their existing science and engineering codes to reflect the reality and, perhaps more importantly, the opportunity of enhanced performance. If you say, I don't need 64-bit precision at this particular point in the algorithm. I remember writing CFD code and realizing that you can dial in the amount of precision you want based on the algorithm you use, how much sophistication you use on say, a stencil of a grid size or something. So there are many opportunities to think about precision in an algorithm that don't all rest predominantly on 64-bit. And the reality is, if you hold on to that like grim death, I think you're going to get left behind, at least for the next few years.
Yeah, I think you make really good points there, Bob. And we should also be looking at how good your model is to begin with, right? Does it make sense to do a lot of really good, exact, high precision calculation on a model that wasn't that precise to begin with, right? So how good is the model? We have to do a lot of software work. But what I don't want to lose the thread of, though, is the importance of, in scientific computing, when we're doing the science, at some point, someone should have to do some math and not just guess. I think science has math as an underpinning, and I would like to be able to do good math as part of science and supercomputing in math. As long as we don't entirely lose sight of someone has to do math and be good at it, then I think there's a lot of room to say, what's the optimal way to do it, and use AI maybe for computational steering or target reduction or post-process analysis. There's a lot of room for AI in HPC. I just don't want it to entirely replace HPC.
Oh, I agree completely. And when we talk about AI, and you brought it up, we don't want to guess. It's my deep unsettled feelings about generative AI at this point, which guesses. Let's be honest, there is lots of hallucinations. There's lots of uncertainty in large language model training. And the discussions I've had with folks is, it's interesting as a recommender system, as a productivity enhancer, but Gen AI is going to be a very difficult road to go down when it comes to science and engineering applications. I was at an SC presentation where some folks were talking about Gen AI and the science and engineering community, and someone mentioned this problem, and swear, guy said, hey, you know what? Sometimes good enough is good enough. And I thought, I hope you're not designing an airplane I'm getting on anytime soon. I think what we need to do is, and I talked to folks about, how do you go about the process of verification and validation in large language models or generative AI kinds of capabilities. So I like to make the distinction between machine learning and deep learning, which has mathematical underpinnings. Certainly machine learning, which is really just really clever data science, and other things. So I'm making a very large distinction between the headline grabbing, staggering kinds of developments that's going on in generative AI versus what's going on in machine learning and deep learning. And I hope that the sector understands that there's a reason to make those distinctions.
We're supposed to be talking about insights from SC24.
Okay.
I'll throw up another one that I was tracking is I think there's been a lot of movement in industry consortia. In particular, you were talking about modular computing. We're hearing a lot about composability. Looking at what's going to go on the interconnect side, particularly with InfiniBand now entirely NVIDIA networking, right? I think Ultra Ethernet Consortium is one of the most important storylines that's out there in terms of how that's going to, what that'll do with high performance Ethernet going forward. I think SNIA is another one that I'm watching. What are your views on the interconnect side?
Yeah. I'm going to completely change the subject, is my view on that,
All right,
because I know
fine.
we only have a certain amount of time here. So I was at a talk that Jay Gambetti, who basically leads quantum computing development at IBM. And there were two interesting facts that came out of that talk. The first one was that's the first time Jay has ever been to an SC conference. The underpinning there is the confluence of quantum and HPC is beginning. People are no longer looking at quantum as an end-all be-all. It's no longer a procedure call, if you will. It's more an instruction in a triple nested do loop. It's got to be integrated into an HPC program. The second point to make is I tried to do a head count of the people that attended at an SC conference, a talk given by the head of IBM Quantum, and I concluded that that was the largest audience I've ever seen at a quantum conference. So if you go to some of the big quantum conferences, you get X hundred people. Jay packed the room. There were more than X hundred people there, showing you that the HPC world is thinking about quantum. They understand that utility class quantum is maybe 3 or 4 years away, but it's time to start thinking about integration, opportunities for your most challenging workloads, and starting to roll up your sleeves and think about how quantum can start to solve my problems in my advanced computing ecosystem.
Oh, yeah. Oh, yeah. And I think we would hear a lot more public excitement about quantum and how close it's getting if people weren't so distracted by the gold rush that is AI right now, which largely isn't overlapping with quantum. And that's been the huge big bang, mostly in the hyperscale side. I'll chip in one more that we haven't talked about as we start wrapping up. I think the big winners really in the near term have been on the data management side. You look at some of the up and comers from, the VASTs and WECAs, and of course DDN was there all along, and Hammerspace is coming up, and Vidura had a big show, and compared to some of your established NetApps and EMCs, et cetera, the storage space is really booming around this, where we're getting 8-figure, 9-figure individual orders for storage. High performance storage for AI is a really exciting area right now. So that's another one that we're watching.
Yeah, exactly. Finally, I know we're supposed to wrap up shortly. But one of the things that jumped out at me at SC, and I just had no idea. For those of us who look at the high level stuff, it seems like a more quotidian kind of activity. There were more companies there talking about liquid cooling, demonstrating immersion. I had no idea it was so hard to make a connector. There were connection companies, there were cooling companies, there were total immersion companies. I think part of it, and one of my colleagues, Mark Nazikoff of the company, here said his summary of SC was either people are doing AI or they're cooling AI, and that pretty much seemed to be kind of the thing. There is
It's a good quip by Mark.
It is. I got to give him credit, unfortunately. The bottom line is, and I live in Ashburn, Virginia, which is where 80% of the internet lives. I'm actually pointing it to, it's back there.
From there.
You would not believe the amount of data centers that are going up that are now 5 or 6 stories tall, liquid cooled, very aggressive. There is a reemergence of new kinds of data center topologies, requirements. It's no longer a sheet metal shed. They're sophisticated, they're aggressive, they're hugely expensive. One of the people that works in the Loudoun County government, which is where the data centers are located, notes that the average homeowner pays $4,000 to $5,000 less each year in property taxes because they're getting all the extra money from the data centers. It's an interesting technology and an interesting tipping point, if you will, or trend, whatever you'd want to call it, a break point in how data centers are designed to meet some of the new requirements going forward. And I think it's an underappreciated aspect what the CSPs are doing in terms of advancing the kind of infrastructure that's required. Certainly power requirements, we're going to see there's a lot of not in my backyard stuff. They want to fire up 3 new coal-fired plants in West Virginia to power the Loudoun County data centers. A lot of issues there. Speaks to that 40 or 50 megawatt system that we start off with. So I'll just stop there.
Yeah.
And
Yeah, you referred to them as CSPs. We tend to use the term hyperscale because hyperscale is so much bigger than just the cloud providing. Jay made reference to YouTube, right? That's part of hyperscale. It's not really cloud. Meta is not a cloud company,
Yeah.
but is one of the biggest hyperscale. So we just look at that. But you're right about this data center build out. We've been tracking it now. 2024 is still in progress. We got a month left, but about 3/4 of all data center infrastructure is going to go to hyperscale companies worldwide this year. And it's really changing the whole dynamic. And we're revisiting our methodology going to next year. So all of these topics, Bob, that I love touching base with you on, this is why we've got this advanced computing community. We're doing them and others, and Google. Thank you for pulling us together for this conversation. We should kick it back over to Jay and Bill.
Yeah, one last thing before we go. You're right. I should be calling it hyperscalers. It is a much more accurate and I think timely. And I will steal that and endeavor to use it more often. All right, Jay, back to you.
Hey
now.
guys, those are great insights, but we have more questions that we want to ask you as well. So Bill, Bill's back online as well. So I want to ask all 3 of you a question that Addison very articulately asked and Bob very deftly dodged about Ultra Ethernet.
Of
That
course.
seems to me to be a tremendous opportunity and potentially one of the remaining equalizers between on-prem systems and cloud systems, depending on adoption of that technology and those solution types. So I really would like each of you to give me, including Bill, who has a long history in the networking space as well, your quick impressions of the prospects for Ultra Ethernet even for fine-grained HPC applications. And I know Bill can't say anything NDA here in this, but the possibility of this in cloud providers and how that might further move his line up in the chart he showed before in terms of the kinds of applications you can address in cloud. So Addison, you asked the question first. Why don't we start with you for your quick assessment of Ultra Ethernet?
Well, I'll try to go very fast. I brought it up because I'm for it in general. And what I really like is that it's, we've already got a foothold with things like HPE Slingshot and BXI V3, which got announced by Evident. These high-end OmniPath at Cornelis, all of these have UEC futures going forward. And I think there's room within it to say there are standard Ethernet underpinnings in terms of how the interconnect's going to work, with room for differentiation for networking at scale, modularity, all of the things that Bob was referring to in terms of how HPC supercomputers of the future are going to need to be built.
Bob,
Yeah,
can't dodge this time.
Okay. By the way, I wasn't deft at all. I leaped out of the way with no finesse. My bottom line on all this is I'm a huge fan of letting 1,000 flowers bloom. I think that what we need are some standard baseline technologies that can be easily adjusted and customized for the workloads at hand, that you can mix and match. I think that interconnects in some sense should enter kind of, in my mind, the plug and play environment, the way so many other things within HPC have gotten. You can literally go to a cafeteria menu and pick the CPU, the GPU, the kinds of interconnects you want, the kind of memory you want. And so having basically a menu, a cafeteria style collection of options that allow you to pick the kinds of hardware requirements that meet your particular workloads. That's my hobby horse for today. The system should reflect the workloads, not the other ways around. And any opportunity that's arise to add more subtleties and more diversity to the kinds of networks or processors or memory or interconnects or storage, that's better for the entire sector. It just makes it much more richer and much more deeper. The vendors don't decide what you get, you decide what you want.
I'll just add, what my favorite oxymoron across all of technology is the phrase competing standards. You know what you don't have if you have competing standards? A standard.
Standard. Yeah.
My definition of a good standard is one that everybody hates, but all for different reasons. And then you know that you've got a good standard. But yeah.
Bill, do you want to comment on the Ultra Ethernet?
I'm going to comment on Ethernet and HPC more generally versus Ultra Ethernet. And I think, Bob hit a good point, which is it's really all about serving the workload. So, I was chairing the TWG for many years, and we realized that we needed the capabilities of InfiniBand available on different wires, and that's what drove the creation of the Rocky standard. We weren't able, unfortunately, due to the charter of the organization, to go solve the end-to-end problem, which is part of why Rocky really didn't take off in certain areas in HPC. The other thing is recognizing workloads are king. Is RDMA is something that was convenient. It was out there. It was built for a different reason, and we made it work in HPC, right? As I referred to earlier, we built early InfiniBand systems. It was never designed for this, and so I think the more groundwork was laid through Open Fabric for the creation of OFI, or libfabric as it's affectionately known, which, back to Bob's point, is about the capabilities the workloads need as opposed to the underlying technology, another level of abstraction. And we've seen how that has created things like OmniPath and Slingshot, right, which have become unburdened by the early InfiniBand standard to better serve the workloads. So I think we have proof that Ethernet can perform at scale. Having standards, of course, is great. One of the biggest challenges, though, is that we couldn't solve the end-to-end problem with Rocky in the InfiniBand Trade Association because we didn't really have a mechanism to get end-to-end congestion control and dealing with packet loss. And so Ultra Ethernet Consortium, of course, is looking to address that problem and bring cloud and Ethernet together. And one of our future topics here, in fact, will be about Google's networking technology in Falcon, which is an RDMA-capable, reliable transport that allows you to build a standards-compliant RDMA engine. So we're pretty excited about the future of Ethernet and HPC. And no, it probably won't be the technology that's used for the highest end, because there's always some tiny messages at scale. But most problems we can address with Ethernet, we believe.
All right, I want to ask one more question of the three of you before I take some of the questions that have been submitted Q&A. You guys, Bob and Addison, you both mentioned at the beginning how we're starting to see these monolithic, homogeneous HPC systems be replaced by more modular systems. One might look at that as a set of diverse computational resources at scale in, say, I don't know, a cloud, for example. So at some level, do you think that the programming paradigms for using these multiple partitions of different types of things will resemble the kinds of cloud workflows and vice versa? Will we start to see a little bit more unity in how we think about using clouds and their diverse subsystems compared to how these large DOE and other systems are programmed and used in workflows with their own individual modules?
I'll jump in quickly because we did a study a while ago for an organization that flat out said we're looking for new HPC, but we undeniably will not think about cloud as an option. And what we ended up doing was kind of spoon-feeding them some things about, well, if you don't like cloud, at least you can start to think about some of the things that cloud brings to the table, like containers, like modular code. So when you decide to change a 1,000,000-line piece of code, you don't have to change a 1,000,000 line. You only have to change a 200-line block of it. And so to me, the idea here is more about each side of the fence learning from the other and adopting some of the best techniques going forward. Certainly a highly partitioned HPC is not around the corner. It's not going to be trivial to move from partition to partition in the early days. Certainly if you're running a hybrid quantum classical system. And God, I always say, please help me if we have something called QMPI for that. We don't need that. So the idea is learning best case examples and adopting them. And I think that there are a lot of things I mentioned: containers, refactorization, modernization, incremental upgrades to software that happen on almost a daily or weekly basis, as opposed to let's not touch this legacy code because it worked 40 years ago. I think there's a lot to be learned from that. And I hope that some of these on-prem software developers, the ones who are helping people access a multi-partitioned heterogeneous architecture, look to the cloud to say, what's the best way to really think about taking advantage of some of the software layers that the cloud brings to the table and how we can make that usable on-prem And what that does in a very covert kind of way is it makes it easier now to have a piece of code that exists equally well, whether you run it on-prem for some applications or some particular hardware requirements, or if you set it up to the cloud. And I think we need to think more about that as well.
Quick replies from Addison and Bill.
Yeah, I think, Bob's statement is well founded. The way I look at your question is that I look at it this way. The number one problem facing the user community for the last many years, a decade, has been one that's not well addressed by any vendor, which is that on the one hand, I've got a diversifying set of workloads. I've got all the scientific computing I've ever had. 10 years ago, I had to start doing big data and analytics. Now I have to do AI. Nobody tripled my budget. And on the other hand, there's a diversifying set of technologies that I might want to bring to bear to solve all of these things. And my big fear is that I'm going to buy some system, and then in 18 months, I'm going to have a new boss who says, what idiot bought all of this stuff, right? That's all underutilized or whatever, right? That is a real problem facing end users. And to say, well, I'm just going to go all cloud. Well, how am I managing the cost of that, right? So there are real questions about what to use where. And to your point, Jay, I think what we're seeing is we're not going to have this homogeneous, well, really, Bob said first, we're not going to have one homogeneous architecture that does everything the best. You start having these specialized components or specialized partitions. What to use cloud for is really just a rent-buy decision on, all right, for this AI partition or this quantum partition or this 64-bit partition or whatever it is, the high memory partition. Do I do that enough and at a high enough of scale that it's worth owning it, or do I rather access it sometimes at a special level of capability in the cloud, particularly when you go to future technologies? Cloud is an ideal sandbox for trying out new architectures that I don't already own, right? Because I want to do a try and buy on something. So cloud is a huge part of balancing out all of these partitions. To say, what do I want to use when for what, and without feeling like I'm really trapped on, well, now I own all of this and it has to be good for everything. So that's kind of a roundabout answer of saying, yeah, cloud is definitely going to fit in here. And it's because of the diversifying technologies have to fit the diversifying workloads.
All right, Bill, do you have a short addition to that?
No, I think it's well covered, and there's a few Q&A from our viewers I'd like us to hit.
Yeah, all right, the number one upvoted question here, and I'm going to ask you all for your quick answers to this so we can try to get through a couple of these before we make our final announcements. How do you expect the hardware requirements to change in the next 5 to 10 years for AI model deploy, i.e. for inferencing and training? Do you think that organizations should make an investment now? Addison, this reminds me of your question, what does my boss say to me 18 months from now about why did you buy this stuff? But phrased a little differently.
I think AI is a really broad term right now, and a lot of AI will be done on thinner and thinner components that get embedded into things at the edge, at the personal device, into your smart thermostat or your refrigerator that's doing AI now. But some of the big heavy-duty training that goes on in hyperscale will persist at very high scale. So it really depends on a lot of what you're talking about here. But you're going to say, here's an AI. What's not part of the AI market right now, right? It's all AI. So, that's a short answer that would just lead into a long answer where we could spend 2 hours talking about it on the next community meeting.
The three biggest buyers of NVIDIA GPUs are the hyperscalers. And all three of those hyperscalers have their own AI chips in development. I think we've forgotten that GPUs used to be called general purpose GPUs. They carry a lot of hardware and a lot of power. What are you talking, 700 watts we're getting up to there? I think that what we're going to see are very much more sophisticated, targeted AI accelerators that don't consume 700 watts, that may be perhaps an order of magnitude less powerful, but all they do is AI for very specific applications. You're going to bare bones custom architectures because the current trends right now in GPU technology is unsustainable. Most people are terrified, not of the technology, but the price it takes to buy into a GPU-based architecture nowadays.
And I'll just add, I think, generalizing the question and the answer, we're entering a new era of specialization. What we talked about with floating point, we talked about GPUs, custom things, and we also have new technologies like chiplets and new standards emerging. So I think that's going to be one of our future topics is what is the trajectory we're on, where are the hazards and where are the opportunities. Since we are in our final 2 minutes here, I thought, Jay, it'd be worthwhile for me to pop through the remaining questions from the audience very quickly and just tee up short answers and future discussions. So let me
And
just do
also,
that.
if Wyatt, you could pull up the next slides too.
I can see those, yeah. Oh, that's right. Okay. So one of the questions is there going to be an opportunity to talk about new cost models for provisioning resources, especially those that are scarce, hard to get? Answer is absolutely yes. I touched on it earlier with some of the changes we're making in the way cloud resources are provisioned. And that will be part of a future topic on provisioning models and accessing and how you assemble supercomputers through simple API calls. Next question was, how do we combine GPUs and with Kubernetes? Referring to that, that's another area of what I considered core HPC technology. We've been investing for the last 4 years to really make Kubernetes engine on Google Cloud HPC capable, not to push you to Kubernetes, but to make it a possible option. So we'll have a dedicated session in the future about the way we're exposing storage, message passing, reducing latency, NUMA controls, hyperthreading, all of the things that we're used to doing in on-prem systems and making those available to you through Kubernetes. That'll be a future session as well. Bill Turner asks, how can I assure my data sets are mine and not shared with other AI models? The short answer there is there's a fundamental difference of when you interact with a chatbot versus when you go into an enterprise AI system. And there are very sophisticated ways that your data is kept private. And that's something we can bring as a topic when we talk about Vertex AI. AI exists all the way from infrastructure up to top of stack type interfaces, and data privacy is paramount. So we'll be able to address that, Bill, in a future session as well. And then the final question from V, I think this is V from Livermore, that I see is, I see another one came in late, is for the scientific climate models you mentioned, if we're moving towards lower precision for AI, is the expectation that we'll need to change our models to use these resources. And this brings us back to the earlier discussion about being left behind. When GPUs came along, the biggest systems were GPUs, and a lot of people were left behind because it was hard to do GPUs. Now that we're seeing a more low precision math, as Bob pointed out, people are being left behind. So there will be a period where I think we're left behind. There isn't an expectation that everyone has to go, and that ties back to the specialization topic. So I think we'll be able to have a really deep discussion on that one in the future as well. With that, I'll hand it back to Jay.